Passive components, phase shifters, series on microwave engineering, lecture number 1.12. Waves, traveling waves. They are associated with phase change, continuous phase change in their journey, in their traveling. The amount of phase shift that exists in the wave per unit length is measured through beta, phase shift constant, with units radians per meter or degrees per meter. Phase shifters are devices which are able to add some more phase to the already existing phase in the wave. The basic design principle, the fundamental idea underlying the functioning of the phase shifters. These are not difficult to understand. In the present session, the focus is on different types of phase shifters, microwave phase shifters, their structural details, their functioning principles, along with their relative merits and demerits. Now, we move further into the course session where we get information or knowledge pertaining to phase shifters from basics to advanced. A few introductory remarks regarding phase shifters. Phase shifters find application in test and measurement microwave systems. The concern here is about phase shifters that are used at microwave frequencies in microwave systems. Their most significant use is in phased array antennas. Phased array antennas, they are critical parts of certain type of radar systems. Phased array antennas are used to steer the antenna beam in space electronically. Beam can be steered mechanically also by employing servo control systems, but it is associated with several disadvantages, in addition being slow, in addition being having wear and tear. The electronic steering of the antenna beam is the latest one, most efficient one, and it is done through electronically controlled phase shifters. Phase shifters which use ferrites in their construction are non-reciprocal, whereas others in general are reciprocal. So most of the phase shifters are reciprocal. A few phase shifters which use ferrites in their design, they are non-reciprocal. The basic principle underlying the design of phase shifters. The basic idea underlying behind the functioning of phase shifters or most of the phase shifters, it can be understood by considering guide wavelength, expression for guide wavelength in hollow pipe waveguides. The amount of phase shift that can be given to a wave of dominant mode by a waveguide section of length L with a hollow region having epsilon r more than 1, mu r more than 1 is given by beta at L equal to 2 pi L by lambda g. Lambda g is guide wavelength. The expression for guide wavelength is lambda naught by square root of 1 minus lambda naught by lambda c whole square. Lambda c can be replaced by 2a when the wave is in dominant mode. Here lambda naught is lambda by square root of mu r epsilon r and can be considered as wavelength that would be in an unbounded medium with constants mu r and epsilon r. So the basic point is the amount of phase shift that occurs in the wave when it travels a length L in a waveguide is given by this formula. Beta is phase shift per unit length. The hat over it indicates that the wave is non-TEM wave. L is length. It is given by 2 pi L by lambda g. Lambda g is given by this form. Now, beta L phase shift, it can be altered, it can be changed by changing lambda g. Lambda g can be changed either by changing lambda naught or lambda c or a. Now, lambda naught. Lambda naught can be varied by varying mu r. Ferrite phase shift oscillator. They are examples for phase shifters where phase shift is varied by employing ferrites whose mu r is large. Lambda naught can also be varied with varying epsilon r. Dielectric phase shifters, they belong to this category. Phase shift beta or L or hat L can also be varied by varying A. Line structures are examples for this category. Before going further, small correction. Epsilon r more than or equal to 1. Mu r more than or equal to 1. With this small correction, the information provided here gives accurate, complete, total information pertaining the underlying principle of functioning of different types of phase shifters. Now, types of phase shifters. Dielectric phase shifters, squeeze type phase shifters, rotary phase shifters, hybrid phase shifters, ferrite phase shifters, fixed phase shift sections. These are all some of the types, varieties, categories of phase shifters that are in use right now. A few points regarding dielectric phase shift. The variable type dielectric phase shifters employ a low loss dielectric insertion into the air-filled guide. The insertion is at a point where the electric field is maximum and the inserted dielectric increases the effective dielectric constant of hollow region, thereby causing the guide wavelength lambda g to decrease. Insertion of the dielectric thus increases the phase shift in the wave passing through the fixed length waveguide section. Tapering of dielectric slab is usually done to reduce the reflections. So basically the basic principle here is epsilon r. It is increased by inserting a dielectric slab into an air-filled guide. Change in epsilon r naturally changes lambda g. Change in lambda g causes phase shift. In another version of dielectric phase shifters, a pair of thin rods is used to move the dielectric slab from a region of low electric field intensity to a region of high field intensity, thus increasing the effective dielectric constant. A typical phase shifter gives minimum phase range of 180 degrees, VSWR of 1.4, insertion loss of 0.4 dB, maximum power rating of 0.6 watts with an insertion length of 3.94 inches at K-band. Notice when the wave is in dominant mode, field intensity is maximum at the center of the waveguide somewhere here. And intensity falls as you move on either side from the center. It falls sinusoidally from maximum to nil at the ends. Effective way of changing effective dielectric constant is inserting the dielectric slab here at the center where field intensity is more. When slab is in the center of the guide where intensity is more, effective constant assumes large values, and when the slab is moved onto either side from the center, dielectric constant becomes less. This is the idea behind the version that is mentioned here. Several phase shifters, they are displayed, illustrated here. A and B are dielectric type, whereas C is a squeeze type. Now A. Notice A, B, C, they all are having a piece of rectangular waveguide as part of their structure. In a slot is cut in the broader wall at the center, and a dielectric slab is being introduced into the guide. A hinge arrangement is there. With the help of this arrangement, different amounts of dielectric slab can be introduced into the guide, thereby ultimately having different amounts of phase shifts. In B, dielectric slab, it is held in position with the help of rods, two rods, horizontal rods. By pulling and pushing these two rods, it is possible to move the plate dielectric slab away from the center of the guide or towards the guide, thereby changing effective dielectric constant, ultimately giving rise to different amounts of phase shift. In C is shown squeeze type. What is a squeeze type? We have seen guide wavelength. It depends upon dimension A also, because lambda C is 2A. Lambda G depends upon lambda C. Lambda C is 2A for dominant mode wave. Changing A naturally changes lambda G, which ultimately causes a change in phase shift. Here A is reduced by pressing the side walls. The slot is cut both in bottom and top broader walls, and the side walls are pushed inside, reducing the value of A. Change in A causes change in lambda G causes amount of phase shift. This is the principle, underlying principle in the functioning of squeeze type phase shifters. A few points regarding squeeze type phase shifters in words. These are also called line stretchers. They consist of a small length of waveguide section whose broader walls contain long non-radiating slots. A clamping arrangement is used to reduce the guide width A, thereby increasing the guide wavelength lambda G, resulting in a decreased phase shift in the wave traveling through the waveguide section. We move on to another type of phase shifters called rotary phase shifters. These are well known for their accuracy. Most accurate right now phase shifters are rotary phase shifters. The essential parts of these shifters are two transitions, rectangular to circular. These transitions can also be called circular to rectangular. Then what are transitions? Transitions are pieces of waveguides, hollow pipe waveguides. They are a cross between rectangular and circular waveguides. In rectangular to circular transition, one opening or one port is rectangular, another port is circular. So, to one end of the transition, one can connect a rectangular waveguide, and to the other end, one can connect circular waveguide. Two such transitions are there in the structure of this device. Three circular waveguide sections, two fixed and one rotary. These are the main components, main parts of the rotary phase shifter. Each one of the two fixed sections carries a quarter wave plate inside, whereas rotary section consists of half wave plate, quarter wave plate, half wave plate fixed inside. All the plates are made out of low loss dielectric, that is sigma conductivity nearly zero, and the plate is usually thin with epsilon r more than 1, mu r equal to 1. Mu r 1 means it is non-magnetic. The device is bidirectional, and hence any one port can be used for connecting the input, and the other then acts as the output port. It is a two-port device. Any one can be used as input port, other port then becomes output port. Here is given the structural details of rotary phase shifter. Here is one transition, let us say input transition. At the other end is another transition, output transition. You see the mouths, the openings are the ports of these transitions are rectangular, circular. One is rectangular, another is circular. In the other transition also. Then we have two fixed quarter wave plates, one on the input side, other at the output side. Notice both are oriented in the same way. They are making an angle of 45 degrees with vertical or horizontal. 45 degrees. 45 degrees. In between quarter wave plate sections, we have one rotatable half wave plate. Length of this section is 2L, where L is length of the fixed section. It is a rotatable section, rotatable part. By rotating, the orientation of the plate inside it can be altered. Here one angle theta m is identified. It is the angle made by the plate from the point which is at 45 degrees from the vertical. Analysis can be done. It is not that much complicated, but here, because of a time constraint, we don't take the analysis, but we concentrate a little bit of time on the result. Input side, a wave is given. Let us suppose its phase is 0, reference. Let us consider the phase of the input wave as a reference. That is the meaning of 0 phase. Let us suppose field intensity is E. Now this wave travels, crosses input fixed quarter wave plate, enters into rotatable half wave plate, and then again it encounters a quarter wave plate. At the other end, it passes through it, enters into the output transition, comes out of the output port. During this journey, the wave undergoes an amount of phase shift that is given by minus 2 theta m minus 4 theta perpendicular L. Theta m is defined here in the diagram. Theta m can also be defined as angle made by the plate with the horizontal minus 45 degrees. From this expression, one can notice by varying theta m, one can have different amounts of phase shifts. L is fixed, beta is fixed. Beta is phase shift constant, phase shift per unit length. A few points regarding the functioning of rotary phase shifters inwards. The presence of the plates, it can be noticed, makes the wave at the output to have an additional phase lag equal to 2 theta m. It is additional phase lag 2 theta m when the half wave plate is rotated by an angle equal to theta m. If the input wave EI is E0, E at an angle of 0, the output wave E0 would be given by E. The amplitude of the wave, it doesn't change while it is passing through the shifter, only phase angle. It is minus 4 beta L minus 2 theta M. Notice this 4 beta L, it is the phase shift the wave undergoes usually or normally. An extra amount is added to this usual or normal phase shift by rotating the rotable section. It adds a phase equal to 2 theta m. The amplitude and polarization of the output E is the same as the input wave, which means that phase shifter is a lossless and reflectionless for any position of the rotary section. The main advantage of these devices is their accuracy, and because of this reason, they are used as calibration standard. These devices have a drawback also. They cannot handle higher power levels. Now we move to another type of phase shifters, namely hybrid phase shifters. For high power applications, hybrid phase shifters are used. The usefulness of rotary phase shifter is limited to lower power levels, few watts or even less. They don't work efficiently, effectively at higher power levels. That is what he is telling. So we have to search for another type of phase shifters. The hybrid phase shifters are the appropriate ones for use at higher power levels. These devices consist of 3 dB short slot coupler and a pair of moving shorts. The coupler divides the input equally between its outputs, but with a quadrature phase difference. The port adjacent to input port is completely isolated from the input port. That is, no part of input wave appears there. So this is the structure shown in A. The functioning is described in B. Two shot, this is one shot, this is another shot. These two are tied together and through a rod. By pushing this rod inside or pulling the rod outside, the position of the shots can be varied. The position varies together. The position of the shots vary in the same manner. This is one port, input port. This is another port, output port. We give signal here. We take the signal from this port. Amplitude of the output signal is equal to amplitude of the input signal, but the phase of the output signal, it can be varied by moving the shots either into the coupler or out of the coupler through the handle to which the shots are connected. Here the functioning is described. Let us suppose a wave is given here at the input port. It travels. As it is a 3 dB coupler, half of it, if it is 1 watt, half of it gets coupled to the coupled port. Only half moves towards the shot. It hits the shot, gets reflected, and then starts traveling towards port 1 or input port. While traveling, again it gets split into two equal, because it is 3 dB coupler. Half of it then moves. So if it is 1, it is 0.5, 0.5. So 0.25, it appears at output port. Remaining 0.25, it goes to 2. From the primary wave, main wave, of course, the wave amplitude here is 0.5. It gets reflected from the shot and then moves like this. While moving, half of it gets coupled to the input port. So 0.25. Here 0.25, here 0.25, these two get added, 0.5. So here 0.5, output is 0.5, 0.25, 0.25, 0.5 returns back to the input port. Input out of the source is 1, 0.5 is coming back, therefore net input is 0.5. So input is 0.5, output is 0.5, okay. But phase of the output or relative phase of the output depends upon the position of the shots. Some points regarding the functioning of hybrid phase shifters. The shots which are perfect reflect the wave completely with gamma, that is a reflection coefficient, -1. These shots are coupled mechanically so that they move as a unit. By shifting shots as a unit, it is possible to vary the phase of the output wave. Moving it back with a distance d causes the output wave to be delayed by an additional 2d, since the round the trip path of the wave is 2d. Thus, the phase change in the hybrid phase shifter is plus or minus 2 beta for d equal to plus or minus 2 pi by lambda gt. This is the formula. The phase change appears to have a linear relationship with the short movement. In practice, lambda or delta theta versus d curve, however, exhibits some deviation from linearity due to imperfect operation of the 3 dB coupler. Typical specification of this phase shifter appear as waveguide size WR42, frequency band 18.3 to 20.2 GHz, power 320 watts average, 3-4 kilowatts peak, VSWR 1.25 maximum, and insertion loss 0.30 dB. Another type of phase shifters are ferrite phase shifters. These shifters employ ferrite rods. These are two-port devices providing variable amount of phase shift with the change in the bias field on the ferrite. One of the most useful designs is the latching or remnant non-reciprocal phase shifter employing ferrite toroid in a rectangular waveguide. Fixed phase shift sections. These are also used in industry, in testing equipment, in laboratory work. To achieve differential phase shift, the guide wavelength is to be altered. We know it can be altered by changing the guide width. Its differential phase shift is given by this part. Differential phase shift can also be produced by inserting reactive elements into the waveguide. In its typical application, three fixed phase waveguide sections are used in the three arms of bridge circuit, while the fourth is a waveguide section in which a phase delay differing from that associated with a standard RWG of equal length is created using differential phase shifters. Here he is describing an application in which fixed phase shift sections are used. These are the things which I have to share with you for right now. To recap, the basic principle underlying the functioning of different types of phase shifters. It is given in the beginning of the session. Then different types of phase shifters, they are introduced and their functioning is described in an elaborate and clear manner. Hope you have a wonderful and beautiful, transformative and enriching learning experience. See you again soon in another session. Enough for now. Bye bye.